Today we'll study sequences. A sequence of real numbers is a function defined on set n, which is set of natural numbers and whose range is contained in the set of real numbers. So any sequence, it is defined by this function f from natural numbers to real numbers. Now you must have studied many sequences. Say for example, arithmetic progression is a sequence. So if we write numbers such as 1, 3, 5, 7, it is an example of a sequence. You might also have heard about this famous Fibonacci sequence, which is 1, 1, and then 1 plus 1, 2, 1 plus 2, 3, 2 plus 3, 5. That is, any term is defined by sum of two previous terms. So this is your Fibonacci sequence. Then there could be some sequences which do not have any mathematical formulation. Say for example, sequence of prime numbers. For sequence of prime numbers, we do not have any formula as yet. Now there are many ways to define a sequence, and the most common way is either using angled brackets and writing its nth term, or using small brackets. Now we have to write any sequence, say for example sequence of reciprocals of even number. Then we can write the sequence as this x and then writing some terms which is 1 by 2, 1 by 4, 1 by 6, 1 by 8, and it goes on. And the other way to express this sequence is writing it as 1 upon 2n, where n belongs to natural numbers. In this first case, we have defined sequence as ordered arrangement of numbers, and the second case, we have defined this in terms of its nth term. Another way to define sequence is using recursive relations. Say for example, let us say, suppose x1 is 1 and xn plus 1 is xn plus 2. Now if we write x2, x2 is 1 plus 2 will be 3. x3 is 3 plus 2, 5. So this sequence is actually sequence of odd natural numbers. So we have defined the sequence of odd natural numbers using a recursive relation, which is xn plus 1 equals xn plus 2, where x1 is 1. Now this Fibonacci sequence, it can be expressed as an plus 1 equals an plus an minus 1. So we may express any sequence by writing ordered terms. We may define a sequence by writing its nth term, or we may define any sequence with recursive formula. And then, as discussed previously, there could be some sequences which do not have any mathematical formulations. Now once we have defined a sequence, the next thing that we'll study is convergence of a sequence. A sequence of real numbers converges to a real number a if for every positive number epsilon there exists an n belongs to natural numbers such that for all n greater than or equal to n, mod of an minus a is less than epsilon. So if we can find any n greater than or equal to n for all the values of epsilon, however small it may be, then we call such a as this limit of sequence, and we write limit n tends to infinite an is equal to a. So this is the formal definition to check convergence of a sequence. So let us take up an example. Now here the question is, show that the sequence fn defined by fn equals under root of n plus 1 minus under root n is convergent. Now one of the limitation of this standard method of checking convergence is we must know this a in order to check convergence using this epsilon method. Now it is not given in the question, but we know that this function fn, it converges to 0. If we take this limit n tends to infinite under root of n plus 1 minus under root n, then it is infinity minus infinity form, and if we multiply it with its conjugate, we'll get this as 1 upon under root of n plus 1 plus under root of n, which is 1 by infinite, and the value of this limit is 0. So this sequence, it converges to this number a, which is 0, and this 0 is the limit of this sequence. Now once we know the value of A, we can use this method to show that the sequence is a convergent sequence. Now we can write mod of fn minus 0. Now mod of fn minus 0 will be mod of under root of n plus 1 minus under root of n. Now what we'll do is we'll rationalize it. We can write this as 1 upon under root n plus 1 plus under root n. Now we know that under root of n plus 1 plus under root n, it is greater than 2 times root n. Then we can write 1 upon under root n plus 1 plus under root n will be less than 1 upon 2 root n. So this expression, it is less than 1 upon 2 root n and it is less than epsilon. Now from this we can write under root n, it is greater than 1 upon 2 epsilon, or n is greater than 1 upon 4 epsilon square, which satisfies our condition that for all the natural numbers which are greater than 1 upon 4 epsilon square, this fn minus 0, it is less than epsilon, however smaller the value of epsilon may be. This is how we show a sequence is convergent using standard definition. Now a sequence, it may be a convergent sequence, and if a sequence does not converge, then we say the sequence is a divergent sequence. So any sequence which does not have a limit or does not converge is said to be divergent. Now what are the conditions that a sequence is divergent? If a sequence, it diverges to plus infinite or minus infinite or more than one limit points, or it have oscillating values, then the sequence is said to be a divergent sequence. Now there are some theorems on divergence, and the first one is if the sequences fn and phi n, they diverge to infinity, then both fn plus phi n and fn into phi n diverge to infinity as well. Second theorem is if fn diverges to infinity and phi n is bounded, then fn plus phi n, it also diverges to infinity. Now third theorem is if fn diverges to infinity and phi n is a convergent sequence, then fn plus phi n, it also diverges to infinity. And the fourth theorem is if we have two sequences fn and phi n such that fn is greater than or equal to phi n and phi n diverges to infinity, then this sequence fn, it also diverges to infinity. And in the same way, if fn is less than phi n and if phi n diverges to minus infinity, then fn also diverges to minus infinity. Let us take up an example. Say for example, let x1 be 1 and xn plus 1 be xn plus 1 upon xn square. Now the first part is show that xn plus 1 cube is greater than xn cube plus 3. Now what we'll do is we'll take cube both sides. We can write xn plus 1 cube and it'll be equal to xn plus 1 upon xn square whole cube. Now it'll be xn cube plus 1 upon xn to the power 6 plus 3, 1 upon xn cube and plus 3. Now since x1 is equal to 1 and xn plus 1 is given by this recursive relation, we can say any xn is greater than 0. And if xn is greater than 0, then xn cube plus 1 upon xn to the power 6 plus 3 upon xn cube plus 3 will always be greater than xn cube plus 3. So that's our first part of the result, which is xn plus 1 cube, it is greater than xn cube plus 3. Now we'll come to this second part, and the second part is we need to prove that xn is greater than or equal to cube root of 3n minus 2. Now for the second part, we need to prove that xn is greater than or equal to cube root of 3n minus 2. Now we'll prove this result using mathematical induction. So we'll prove this result when n is 1. So we can write x1, it is greater than or equal to cube root of 3n minus 2, and here the value of n is 1, so it will be greater than or equal to 1, and the question it says x1 equals to 1, that means p1 is true. Now we'll let pk be true. Now if pk is true, then we can write xk and it will be greater than or equal to cube root of 3k minus 2. Now we have to prove this result for pk plus 1. Now for pk plus 1, we need to write xk plus 1. Now we know that xk plus 1 cube, it will be greater than xk cube plus 3, and this xk, it is greater than or equal to this 3k minus 2. So we can write this as 3k minus 2 plus 3. So from here we can write xk plus 1, it will be greater than or equal to 3k plus 1 minus 2 whole cube root. That means pk plus 1 is true. So from induction we can say that xn will always be greater than or equal to cube root of 3n minus 2. Now this third part is show that xn diverges. Now in part B, we have already shown that xn is greater than or equal to cube root of 3n minus 2. Now if we take this limit n tends to infinite, cube root of 3n minus 2, we know that this limit, it diverges to plus infinite. And since xn is greater than fn and fn, it diverges, from here we can say that this xn also diverges to infinity using theorems on divergence. So from here we can say that the sequence xn diverges. Let fn and gn be two sequences such that fn plus gn and fn into gn converge. Show by an example that the sequence fn and gn may fail to converge. Now let us take an example where fn is minus 1 to the power n and gn is minus 1 to the power n plus 1. Now we look at fn plus gn. fn plus gn, in this case it will be simply 0, and this constant sequence, it always converges to 0. Whereas both fn and gn, they have oscillating values at infinity, plus 1 and minus 1, and both these sequences, they do not converge. So it is an example in which fn plus gn, it converges, but fn and gn, they both fail to converge. Now considering the same example, if we take fn into gn will be minus 1 to the power 2n plus 1, and which is simply minus 1. Now again it is a constant sequence. Now this constant sequence again, it converges to minus 1, whereas both fn and gn, they fail to converge. So this is one such example. Now let us look at two very important sequences. Now the first one is bounded sequence. A sequence is said to be bounded above if there exists a natural number n such that an is less than or equal to n for every n greater than or equal to 1. That is, all the terms of the sequence, they are always less than or equal to some number n. In the same way, we can say a sequence is bounded below if all the terms in the sequence, they are greater than or equal to some number m for all n greater than or equal to 1. And we say that a sequence is bounded if it is both bounded above as well as bounded below. That is, all the terms of the sequence, they are greater than or equal to some number m, but less than or equal to some number n. Then we say the sequence is bounded. And one of the important properties of convergent sequences, every convergent sequence is bounded. So if there is a convergent sequence, then that sequence has to be a bounded sequence. Now let us take monotonic sequences. Now when we say a sequence is monotonic, we simply mean that either it is an increasing sequence or it is a decreasing sequence. So we say any sequence xn, which is a sequence of real numbers, is increasing if x1 is less than equal to x2, is less than equal to xn, is less than equal to xn plus 1. So this sequence, we say it is an increasing sequence. In the same way, if x1 is greater than or equal to x2 and xn is greater than or equal to xn plus 1, we say that the sequence is decreasing. A sequence is said to be monotone if it is either increasing or decreasing. So if we have to prove any sequence is a monotone, we need to prove that either it is increasing or it is decreasing. Now let us take up a question. It says, using induction, prove that the sequence a1 equals 1 and an plus 1 equals 3 minus 1 upon an is an increasing sequence. Now we are given that an plus 1 is 3 minus 1 upon an. Now we can find a2 and a2 will be 3 minus 1 upon a1 and the value of a1 is 1. So a2 is 2. Now our statement is the sequence is increasing. That means an plus 1 is greater than or equal to an. Now we'll prove the statement for n equals 1. Now if the value of n is 1, then we can write a2 is greater than or equal to a1. Now a2 is 2 and a1 is 1. So this statement 1 is correct. Now let us assume that let pk be true. If pk is true, then we can write ak plus 1 will be greater than or equal to ak. Now 1 upon ak plus 1 will be less than or equal to 1 upon ak. Now we multiplied with minus 1, we can write 1 upon ak plus 1 will be greater than or equal to minus 1 upon ak, and then we'll add 3 both sides. Now this is nothing but this is ak plus 2. So from here we can say ak plus 2 is greater than or equal to ak plus 1. That means p k plus 1 is true. So from mathematical induction we can say that an plus 1 will always be greater than or equal to an for all n belongs to n. That is, the sequence is an increasing sequence. Now let us take another question. It says, is the sequence 2 to the power n upon factorial n is a monotonic non-increasing or non-decreasing sequence? And find the bounds of this sequence. Now for this question, an is given by 2 to the power n upon factorial n. Now we write an plus 1 upon an. Now an plus 1 will be 2 to the power of n plus 1 upon factorial n plus 1, and then divide by an, which is 2 to the power n upon factorial n. Now here 2 to the power n will cancel. Now factorial n will also cancel. So we'll get this as 2 upon n plus 1. That is an plus 1 upon an, and it is equal to 2 upon n plus 1. Now n plus 1 is always greater than or equal to 2. That means 2 upon n plus 1, it is always less than or equal to 1. So from here we can say that an plus 1 is less than or equal to an. That means the sequence is decreasing sequence or monotonic non-increasing sequence. Now we have to find bounds of this sequence. Now we know that an is defined as 2 to the power n upon factorial n, and it is always greater than 0. Now we need to find its upper bound. Now we know that factorial n, it is always greater than or equal to 2 to the power of n minus 1. So in general, factorial n is always greater than or equal to 2 to the power of n minus 1. So 1 upon factorial n will be less than 1 upon 2 to the power of n minus 1. So we can write this an will be less than or equal to 2 to the power n upon 2 to the power of n minus 1. That is, the sequence is always less than or equal to 2. So from here we can say the sequence is a bounded sequence. Now here the question is, state whether xn, which is given by n plus 1 upon n, is monotonic increasing or decreasing. Now we can write xn plus 1 minus xn is n plus 2 upon n plus 1 minus n plus 1 upon n. Will be n square plus 2n minus n square minus 2n minus 1 upon n into n plus 1. Now here n square and 2n will cancel. So we'll get xn plus 1 minus xn, and it will be equal to minus 1 upon n into n plus 1, which is less than 0. So from here we can say xn plus 1 is always less than xn. That means the sequence is monotonic decreasing. Now another method to show the sequence is decreasing is by considering this function fx equals 1 plus 1 by x. Now if we find f dash x will be minus 1 upon x square. That means f dash x is less than 0. And if f dash x is less than 0, then fx is strictly decreasing. So this function fx, it is strictly decreasing function. So if we plot the graph of this function will be strictly decreasing when x is greater than 0. Now, if we look at the sequence xn, which is n plus 1 by n, it is nothing but 1 plus 1 by n. That is, it is the same function only defined for natural numbers. So if we consider the value of this function at natural numbers, then this function, it is strictly decreasing for natural numbers also. So this xn, it is monotonic decreasing. And this leads to our most important theorem, and that is monotone convergence theorem. And the theorem says any monotonic sequence of real numbers is convergent if and only if it is bounded. So if we can show that any sequence which is monotone and bounded sequence is a convergent sequence. So while discussing convergence of a sequence, what we'll do is we'll prove that a sequence is monotonic and the sequence is bounded. Now let us take up an example. Say for example, we are given that let a1 equals root 2 and an plus 1 is under root an plus 2 for n greater than or equal to 1. Now the first question is prove that an is less than 2 for all n belongs to n. Now we'll prove this first part using induction. So our assertion is Pn, which is an is less than 2. Now we'll prove this result for P1. Now we take n as 1, we'll get a1, and the value of a1 is root 2 and root 2 is less than 2. That means statement 1 is correct. Now we'll let pk be true. That means ak is less than 2. Now using pk, we have to prove that pk plus 1 is also true. Now we are given that ak is less than 2. If we add 2 both sides, we can write ak plus 2 will be less than 4. That is under root of ak plus 2 will be less than 2. Now under root of ak plus 2 will be nothing but ak plus 1. So from here we can say ak plus 1 will be less than 2. That means pk plus 1 is true. And if pk plus 1 is true, from induction we can say that it is a bounded sequence. Now second part is we need to prove that this an, it is an increasing sequence. Now we are given that a1 is root 2 and an plus 1 is under root of an plus 2. We have to prove that this sequence is an increasing sequence. That is an, it is less than or equal to an plus 1. Now for this part also we'll use induction. So this is our assertion. And first we'll prove it for n equals 1. For n equals 1 we'll get a1 is less than or equal to a2. Now a1 is root 2 and a2 is under root of 2 plus root 2. Now under root of 2 plus root 2, it is greater than root 2. So from here we can say a2 is greater than a1. That is this assertion is true for n equals 1. Now we'll let pk be true. Now if pk is true, then ak, it will be less than or equal to a k plus 1. Now what we'll do is we'll add to both sides. We'll write 2 plus ak, it will be less than or equal to 2 plus ak plus 1. And if we take under root sign also, then under root of ak plus 2 will be less than or equal to under root of 2 plus ak plus 1. Now this is nothing but this is ak plus 1 and it will be less than or equal to ak plus 2. That means assertion pk plus 1 is true. So from induction we can say that this sequence is an increasing sequence. So now we have this result that this sequence, it is bounded as well as it is monotonic. So from monotone convergent sequence we can say that it is a convergent sequence. Now we need to find limit of the sequence. Now since we know that the sequence is a convergent sequence, then this limit n tends to infinite an will be equal to this limit n tends to infinite an plus 1 and this is say L. Now in this recurring relation, what we'll do is we'll take limit n tends to infinite both sides. So if we take n tends to infinite both sides, we can write L equals under root of L plus 2, that is L square minus L minus 2 equals 0. Now from here we can say either the value of L is 2 or the value of L is minus 1. But L cannot take the value minus 1 because A1 is root 2 and the sequence is increasing. So the limiting point, it must have a value which is greater than root 2. That means in this case, the value of limit point will be 2. So we can say that this limit n tends to infinite an, its value will be simply 2. Now here the question is, let y be defined inductively by y1 equals 1 and yn plus 1 equals 1 by 4 2yn plus 3 for all n greater than or equal to 1. Now we need to show that the sequence is converging and it converges to 3 by 2. Now y1 is 1. We can write y2. y2 will be 1 by 4 2 plus 3 5 by 4. Now in the first part we'll prove that the sequence is monotonic increasing sequence, that is yn is less than or equal to yn plus 1. So this is our assertion. Now we'll prove this result for n equals 1. So for n equals 1, we'll get y1 is less than or equal to y2. Now y1 is 1 and y2 is 5 by 4. So clearly 1 is less than 5 by 4. That means p1 is true. Now we let pk be true. So if pk is true, then we can write yk, it is less than or equal to yk plus 1. Now we multiply it with 2 and then add 3, we can write 2yk plus 3 will be less than 2yk plus 1 plus 3 and we'll divide everything with 4. So we'll get 1 by 4 of this first expression less than equal to 1 by 4 of this second expression. Now this is nothing but this is yk plus 1. So we can write yk plus 1 will be less than or equal to yk plus 2. That means assertion pk plus 1 is true. So from mathematical induction we can say that this sequence, it is monotonic increasing sequence. Now the second part we'll prove that the sequence is a bounded sequence. So y1 equals 1 and yn plus 1 equals 1 by 4 2yn plus 3. Now for the second part also, we'll make the assertion that yn, it is less than 2 for all n belongs to n. So that's our assertion pn. Now we'll prove it for n equals 1. Now for n equals 1, we'll get y1 and y1 is 1 and y1 is less than 2. That means p1 is true. Now we'll let pk be true. That means yn is less than 2. What we'll do is we'll multiply it with 2 and then add 3. So we'll get 2yn plus 3. It is less than 2 into 2 4, 4 plus 3 is 7 and we multiply it with 1 by 4. So we'll get yn plus 1, it is less than 7 by 4 which is less than 2. So that means P k plus 1 is also true. So from mathematical induction, we can say that this sequence, it is a bounded sequence where each and every term is bounded between 0 and 2. Now we need to find limit point of the sequence. Now for limit point of the sequence, we'll take limit n tends to infinite. Now we know that the sequence is both monotonic and bounded. So this sequence, it must be a convergent sequence, and suppose it converges to some limit L. So this limit yn plus 1 will be L, and then limit n tends to infinite yn will also be L. So we can write L equals 1 by 4 2L plus 3. So it will be 2L equals 3, or the value of L is 3 by 2. So this sequence, it will converge to 3 by 2, that is the value of this limit n tends to infinite yn will be 3 by 2. Now here the question is, show that the sequence under root 2, under root 2 root 2, under root 2 root 2 root 2 converges, and find its limit. Now for this question, a1 is 2 to the power 1 by 2, a2 is 2 to the power 1 by 2 plus 1 by 4, a3 is 2 to the power 1 by 2 plus 1 by 4 plus 1 by 8, that is an is 2 to the power 1 by 2 plus 1 by 2 square up to 1 by 2 to the power of n. Now this power is nothing but a GP, so we can write 2 to the power 1 by 2, 1 minus 1 upon 2 to the power n upon 1 minus 1 by 2. This 1 by 2 will cancel, so we'll get this as 2 to the power 1 minus 1 upon 2 to the power n, and it will always be less than 2. So we can write this an, it is greater than 0 but less than 2, that is the sequence is a bounded sequence. Now we will prove that the sequence is a monotonic sequence. Now we know that 2 to the power n, it is less than 2 to the power of n plus 1 minus 1 upon 2 to the power n, it will be less than minus 1 upon 2 to the power of n plus 1, and we can write 2 to the power of 1 minus 1 upon 2 to the power n, it will be less than 2 to the power 1 minus 1 upon 2 to the power of n plus 1. That means an will be less than an plus 1, that is the sequence is monotonic increasing sequence. Now since the sequence is bounded and monotonic, then from monotone convergence theorem we can say that the sequence converges, and we need to find its limit. Now we'll take this limit n tends to infinite. If we take this limit n tends to infinite, it will be an infinite GP. Then this value will be 2 to the power a upon 1 minus r, and there will be simply 2. So this sequence, it converges to 2. So its limit will be simply 2. Now another method to solve the same question is using recursive relation. Now here a1 is root 2 and an plus 1 is root 2 into an. Now in the first part, we'll prove that this sequence is a bounded sequence, and our assertion is an is less than 2. So that's your Pn. Now we'll prove the result for n equals 1. So we'll write a1, and a1 is root 2 and root 2 is less than 2. That means it is true for n equals 1. Now we'll let pk be true. It means that ak, it will be less than 2. Now we'll multiply ak with 2. So we'll write 2ak will be less than 4. Then under root of 2ak, it will be less than 2, and root 2ak, it is nothing but ak plus 1. So from here we can say ak plus 1 is less than 2. That means pk plus 1 is true. So from induction we can say that this an is less than 2, or this an is greater than 0 but less than 2, that is the sequence is a bounded sequence. Now for the second part, we'll prove that the sequence is monotone increasing sequence, that is an, it will be less than an plus 1. So that's your assertion Pn. We'll prove this assertion for n equals 1. So for n equals 1, we'll get a1, and a1 is root 2, which is less than under root of 2 root 2, which is a2. That is, a1 is less than a2. That means it is true for n equals 1. Now for the second part, we let pk be true. So if pk is true, then ak will be less than ak plus 1. Now we'll multiply it with 2 and we'll take under root sign. So we'll write under root 2 ak will be less than under root 2 ak plus 1. Now this is nothing but ak plus 1 and this is ak plus 2. So from here we can say p k plus 1 is true. So from mathematical induction we can say that an will be less than an plus 1 and that the sequence is monotonic increasing sequence. Now since we have proved that the sequence is bounded and monotonic, then from monotone convergence theorem we can say that this sequence is a convergent sequence. Now we need to find its limit. So using this recursive relation, we'll take limit n tends to infinite, and if the sequence converges to some limit L, we can write L equals under root 2L. That is, the value of L is simply 2. So the sequence, it converges to 2. So that's our second method of solving this question. Now here the question is, an is a sequence of real numbers satisfying an plus 1 equals 3an upon 2 plus an. We need to prove that if a1 lies between 0 and 1, then the sequence is increasing, and if a1 is greater than 1, then the sequence is decreasing. And hence we have to prove that this limit n tends to infinite an is equal to 1. Now what we are given is, we are given that an plus 1 is equal to 3an upon 2 plus an. Now since each of the case a1 is greater than 0, we can say that any an plus 1 will be greater than 0. Now we can rearrange this as 1 upon an plus 1 will be equal to 2 plus an upon 3an, and we can also write this as 1 upon an plus 1 will be equal to 1 upon 3 plus 2 upon 3an. Now what we'll do is, we'll subtract 1 both sides. We can write this as 1 upon an plus 1 minus 1 will be equal to 2 by 3 1 upon an minus 1. So we have this relation which is an plus 1 minus 1 and it will be equal to 2 by 3 1 upon an minus 1. Now using this recurring relation, we can prove that 1 upon an plus 1 minus 1 will be equal to 2 by 3 to the power n 1 upon a1 minus 1. Now we'll take this first case when a1 lies between 0 and 1. Now if a1 lies between 0 and 1, then 1 upon a1 will be greater than 1. 1 upon a1 minus 1 will be greater than 0. If 1 upon a1 minus 1 is greater than 0, then from here we can say 1 upon an plus 1 minus 1 will also be greater than 0. So this expression will be positive and this expression also will be positive. So we'll start with this one. We are given that 1 upon an plus 1 minus 1 and it is equal to 2 by 3 1 upon an minus 1. Now it will be less than 1 upon an minus 1. Now if we compare these two, we'll get 1 upon an plus 1 will be less than 1 upon an, and since each term in the sequence is positive, we can say that an plus 1 will be greater than an. That is, this sequence an is increasing. So we have proved that this sequence is an increasing sequence. Now for the second part, if we take a1 greater than 1, so if we take a1 greater than 1, 1 upon a1 will be less than 1. That means 1 upon a1 minus 1 will be less than 0. And if 1 upon a1 minus 1 is less than 0, then 1 upon an plus 1 minus 1 will also be less than 0. Now for this case, both these expressions, they'll be negative. So we are given that 1 upon an plus 1 minus 1 will be equal to 2 by 3, 1 upon an minus 1, and will be greater than 1 upon an minus 1. Now again comparing these two, we'll get 1 upon an plus 1 will be greater than 1 upon an, that is an plus 1 will be less than an. That is, when a1 is greater than 1, then this sequence is a decreasing sequence. So in the first case, when a1 lies between 0 and 1, the sequence is increasing, and when a1 is greater than 1, the sequence is a decreasing sequence. We can also write that this an plus 1 is 3an. Now we'll add 6 and subtract 6 upon 2 plus an. Then this an plus 1 will be 3 minus 6 upon 2 plus an. Now this value will be always less than 3. So an plus 1 will be greater than 0 but less than 3. That means terms of the sequence, they are bounded. So the sequence is monotonic as well as bounded. Then using monotone convergence theorem, we can say that it must converge to some limit L. Now in both the cases, we need to prove that limit of the sequence is 1. Using recurring relation, we can write 1 upon an minus 1 will be equal to 2 by 3 to the power n minus 1 upon a1 minus 1. Now if we take this limit, n tends to infinite, this limit will be 0. So we can write limit n tends to infinite 1 upon an, it is equal to 1. So from here we can say this limit n tends to infinite an will be simply 1. Now here the question is, if a and b, they are positive numbers such that a is less than b and the sequence an be recursively defined as an plus 1 equals an square plus ab upon a plus b, where a1 equals c and it is greater than 0. Now the first part is, if c lies between a and b, then by induction show that an, it will lie between a and b for all values of n. Now we have to prove this statement using induction. So our assertion is, any term in the sequence an, it will lie between a and b. Now we have to prove this statement for n equals 1. Now if we take n equals 1, we'll get a1 greater than equal to a but less than equal to b. And the question, it says this a1 is c and c lies between a and b. That means p1 is true. Now we'll let pk be true. So we can write ak will lie between a and b. Now we square it, we'll write a square will be less than or equal to ak square and will be less than equal to b square. Now we'll add ab, so we'll write a square plus ab will be less than ak square plus ab plus b square plus ab, and now we'll divide everything with a plus b. Now we divide everything with a plus b, we'll get a is less than ak square plus ab upon a plus b and will be less than or equal to b. That is, this ak plus 1 will also lie between a and b. That is, p k plus 1 is true. So p1 is true, and assuming pk to be true, we have proved that pk plus 1 is true. So from induction we can say that any term of the sequence will lie between a and b. That is, this sequence is a bounded sequence. Now for the second part, we have to prove that this sequence is a decreasing sequence. Now for the second part, what we'll do is we'll write ak plus 1 minus ak. Now ak plus 1 is ak square plus ab upon a plus b minus ak. So it will be ak square minus a plus b ak and then plus ab upon a plus b. Now we can factorize this as ak minus a into ak minus b upon a plus b. Now we know that ak, it lies between a and b. That means this value will be positive and ak minus b will be negative. So this expression is less than or equal to 0. So from here we can conclude that ak plus 1 minus ak will be less than equal to 0. That is, ak plus 1 is less than or equal to ak. That is, the sequence an is a decreasing sequence. Now since we have proved that the sequence is bounded and it is monotone decreasing, we know that the sequence converges. Now we have to find its limit point. So what we'll do is we'll take this limit n tends to infinite. So let the limit point of the sequence be L. So this is L equals, and then this limit n tends to infinite an will also be L. So it will be L square plus AB upon A plus B. We'll get L square minus A plus BL plus AB equals 0. So the value of L is either A or the value of L is B. Now we are given that A1 is C, and this C, it lies between A and B, and the sequence is decreasing. That means this limit point, it should be less than B. So limit point of the sequence will be simply A. That means this limit n tends to infinite an, limit point of the sequence is nothing but A. Now for the second part, if C is greater than B, that is, if A1 is greater than B, then A2 will be A1 square plus AB upon A plus B will also be greater than B. So from induction we can prove that any AN will be greater than B. Now in this case, if we write AN plus 1 minus AN, it will be simply AN minus A into AN minus B upon A plus B. Now since AN is greater than B, this is positive and this is positive, so it will be greater than 0. So from here we can say AN plus 1 will be greater than AN. Now in this case, this sequence will be an increasing sequence. So this sequence A1, A2, A3 will increase, and this A1 is greater than B. Now let us suppose that this sequence, it converges to some limit L. Then again, using the same fundamental, we can write L square plus AB upon A plus B equals L. That is, the limit point of the sequence will be either A or B. But in this case, A1 is greater than B and the sequence is an increasing sequence. So its limit point, it must be greater than B. So this limit point cannot be A, and this limit point, it cannot be B. So from here we can say that in this case, when C is greater than B, this sequence, it does not converge by contradiction. Now here the question is, if A and x0 are positive real numbers and xk be defined as follows, xk equals 1 by 2 xk minus 1 plus A upon xk minus 1, then prove that xk is monotone decreasing and bounded, and then calculate the limit. Now x0, it is given that x0 is greater than 0, then x1 will also be greater than 0. So any term in the sequence, say xk, it will be greater than 0. Now if we write this xk as xk minus 1 plus A upon xk minus 1 by 2, then we know that arithmetic mean is always greater than or equal to its geometric mean, and its geometric mean will be under root of xk minus 1 A upon xk minus 1. So this xk minus 1 will cancel. So from here we can say this xk, it will be greater than or equal to under root a. That means the sequence is bounded below. Now we'll find xk minus xk minus 1 will be xk minus 1 plus a upon xk minus 1 divided by 2 minus xk minus 1. So we can write this as a minus xk minus 1 whole square upon 2x k minus 1. Now xk minus 1 will be greater than or equal to under root a. So this a minus xk minus 1 square, it should be less than or equal to 0. So from here we can say this xk, it should be less than x k minus 1. That is, this sequence is monotone decreasing sequence. Now the sequence is bounded below and it is a decreasing sequence. That means the sequence, it converges. So if it converges, now let us say it converges to limit L. So if we take this limit k tends to infinite, then we can write L equals 1 by 2 L plus a by L. That is L square equals a, or the value of L is plus or minus under root a. Now the sequence, it contains positive terms. So the limit point of the sequence will be under root a. So this limit k tends to infinite, ak will be simply under root a. Now here the question is, show that the sequence an defined by an plus 1 equals 1 by 2 an plus 9 upon an, where n is greater than or equal to 1 and a1 is greater than 0, it converges to 3. Now we are given that an plus 1 equals 1 by 2 an plus 9 upon an. Now any term of the sequence, it is a positive number. Now if we write an plus 1 as an plus 9 upon an by 2, then arithmetic mean, it is always greater than or equal to its geometric mean, which is 3. So this an plus 1 will be greater than or equal to 3. Now if we write an plus 1 minus an will be simply 9 upon an minus an by 2 will be 9 minus an square upon 2an. Now since an is greater than or equal to 3, 9 minus an square is always less than or equal to 0. That means an plus 1 will be less than or equal to an. That is, this sequence is monotone decreasing sequence. Now since the sequence is bounded below and it is monotone decreasing, it is a convergent sequence. Now we need to find limit of the sequence, and let the limit point be L. We can write L equals 1 by 2 L plus 9 by L. So from here we'll get the value of L as simply 3. Simply 3 because we have to take positive value of this limit point. So this limit, it converges to 3, and that is the answer to this question. Now the next question is, show that the sequence Sn, which is 1 plus 1 by n to the power n, is convergent, and then we need to prove that this limit, it lies between 2 and 3. Now using binomial expansion, we can write Sn as 1 plus n into 1 by n minus 1 upon factorial 2, 1 upon n square, n minus 1, n minus 2 upon factorial 3, 1 upon n cube. Now here n and n will cancel. So we can write this Sn as 2 plus 1 upon factorial 2, 1 minus 1 by n plus 1 upon factorial 3, 1 minus 1 by n, 1 minus 2 by n, and then the sequence continues. Now this sequence, it is an increasing function of n. So this sequence is an increasing sequence. And since this is 2 plus some positive value, we can say that this Sn, it will always be greater than 2. Now we need to prove that it is less than 3. Now what we'll do is, we'll write as n tends to infinite, this 1 upon factorial 2, it will be less than or equal to 1 by 2. This 1 upon factorial 3, it will be less than 1 upon 2 square. Next one will be less than 1 upon 2 cube. So from this we can write this Sn will be less than 2 plus 1 by 2 plus 1 by 2 square plus 1 by 2 cube up to infinite. This is nothing but an infinite GP. We can write this as 2 plus a upon 1 minus r, which is 3. So from these two conditions we can say that the sequence is bounded and its value will lie between 2 and 3. So the sequence is monotone increasing and it is bounded. That means the sequence, it is a convergent sequence and the limit of the sequence will lie between 2 and 3. We can find the limit of the sequence also. We can write this limit as limit n tends to infinite Sn, and it will be this limit n tends to infinite 1 plus 1 by n to the power n. Now we can write this as limit n tends to infinite e to the power log 1 plus 1 by n to the power n, which we can write as e to the power this limit n tends to infinite log 1 plus 1 by n upon 1 by n. Now this is standard limit, log 1 plus x upon x, which is 1. So the limit point of the sequence is e, whose value is 2.7 something, which lies between 2 and 3. Now here the question is, show that the sequence Sn defined by S1 equals 1 and Sn plus 1 equals 4 plus 3 Sn upon 3 plus 2 Sn is convergent and find its limit. Now what we'll do is, we'll write this Sn plus 1 as 1 by 2 and then 6 Sn plus 8 upon 3 plus 2 Sn. Now what we'll do is, we'll add 9 and subtract 9. We can write Sn plus 1 as 1 by 2. Now here we'll take this 3 common, so it'll be 3 and then minus 1 upon 3 plus 2 Sn. So this Sn plus 1 will be 3 by 2 minus 1 by 2 into 3 plus 2 Sn. Now any term in the sequence, it is greater than 0. So we can write Sn plus 1 will be greater than 0 and will be less than 3 by 2. So this sequence, it is a bounded sequence. Now using induction, we'll prove that this sequence is monotonic increasing sequence. Now if we write S1, S1 is 1 and S2 will be 4 plus 3 upon 3 plus 2, which is 7 by 5. Here our assertion is Pn is Sn plus 1 will be greater than Sn. Now we'll let Pk be true. That means Sk plus 1, it will be greater than Sk. Now we'll multiply it with 2 and we'll add 3. We can write 2Sk plus 1 plus 3 will be greater than 2Sk plus 3. Now we'll take the reciprocal and we'll multiply it with minus 1 by 2. So we can write minus 1 by 2 2Sk plus 1 plus 3. It will be greater than minus 1 by 2 2Sk plus 3, and then we'll also add 3 by 2 both sides. Now this is nothing but this is sk plus 2 and this one here is sk plus 1. So from here we can say that p k plus 1 is true. So from mathematical induction we can say that this sequence is monotonic increasing sequence. Now since the sequence is bounded and it is monotone increasing, it is a convergent sequence. Now we need to find limit of this sequence. Now let the limit of the sequence be L. So we can write L equals 4 plus 3L upon 3 plus 2L. So we'll get 2L square equals 4. Then the value of L is simply root 2. So limit of the sequence will be root 2. Now here the question is, prove that the sequence whose nth term is an equals under root of n plus 1 minus under root n, it is monotonic, it is bounded and it is convergent. Now we can write this an as 1 upon under root of n plus 1 plus under root n. Now this value will be less than 1 upon 2 root n, which is less than 1 by 2. So from here we can say this an, it will lie between 0 and 1 by 2. That is, the sequence is a bounded sequence. So the sequence is a bounded sequence. Now we need to prove that sequence is monotonic. Now we know that under root of n plus under root of n plus 1 will be less than under root of n plus 1 plus under root of n plus 2. Now we take the reciprocal, we can write 1 upon under root n plus under root n plus 1 will be greater than 1 upon under root of n plus 1 plus under root of n plus 2. That is an, it is greater than n plus 1. That means this sequence is monotonic decreasing sequence. So this sequence is monotonic. Now monotone convergent sequence says if the sequence is bounded and monotonic, then the sequence is a convergent sequence. So we can say that the sequence, it converges. Limit of the sequence is limit n tends to infinite an, which is this limit n tends to infinite 1 upon under root of n plus 1 plus under root n, which is 0. So this sequence, it converges to 0. Now here the question is, let an be a sequence defined as a1 equals 3 by 2 and an plus 1 equals 2 minus 1 upon an. Now from here we can write a2 equals 2 minus 1 upon an, which is 2 by 3. So it will be simply 4 by 3. Now we'll prove two results. First we'll prove that the sequence is bounded below. That is an, it is greater than 1. So this is our assertion Pn. Now we'll prove this result for n equals 1. We'll get a1. a1 is 3 by 2, which is greater than 1. That means p1 is true. Now second step is let pk be true. It means ak, it will be greater than 1. If ak is greater than 1, 1 upon ak will be less than 1 and minus 1 upon ak, it will be greater than minus 1. Now we'll add 2 to it. Now this is nothing but this is ak plus 1. So from here we can say ak plus 1 will be greater than 1. So this sequence is bounded below and an is greater than 1. Now the second part we'll prove that this sequence is monotonic decreasing sequence, that is an plus 1 will be less than an. Now here this is our Pn. Now for n equals 1 we'll get a2, and a2 is 4 by 3 which is less than 3 by 2, and that is a1. So that means p1 is true. Now second step, let pk be true. Now if pk is true, it means ak plus 1 will be less than ak. Now if we take a reciprocal, we can write 1 upon ak plus 1 will be greater than 1 upon ak. Now we multiply with the minus sign and then add 2. We can write 2 minus 1 upon ak plus 1 will be less than 2 minus 1 upon ak. This is nothing but this is ak plus 2 and it is less than ak plus 1. That means p k plus 1 is true. So from mathematical induction we can say that this sequence is monotone decreasing sequence. So the sequence is bounded below and it is monotone decreasing. Then we can say that this sequence, it is a convergent sequence. Now we need to find limit of convergence. Now suppose the limit is L, we can write L equals 2 minus 1 by L. Now this is L square minus 2L plus 1 equals 0. That is the value of L is 1. So this sequence converges and it converges to 1. Now here the question is, if Sn is a sequence such that Sn plus 1 equals under root AB square plus Sn square upon A plus 1, where B is greater than A and S1 equals A greater than 0, then show that this sequence is an increasing bounded above sequence and this limit n tends to infinite Sn is equal to 1. Now we are given that S1 is equal to A and it is greater than 0. Now if we put the value of S1, we'll get S2. Any term in the sequence, it will be simply greater than 0. Now we square this one, we can write Sn plus 1 square will be AB square plus Sn square upon A plus 1, and if we write Sn plus 1 square minus Sn square will be simply AB square plus Sn square minus A Sn square minus Sn square upon A plus 1. Now this Sn square will cancel. We can write this as A into B square minus Sn square upon A plus 1. Now A is a positive number. So from here we can write this expression will be less than B square minus Sn square. Now we compare these two, we can write Sn plus 1 square, it will be less than B square. That is, the sequence is bounded above. So any term of the sequence, it will be greater than 0 but less than B. Now since Sn plus 1 is less than B, that means B square minus Sn square will be positive. So from here we can say Sn plus 1 square minus Sn square, it will be greater than or equal to 0. That is Sn plus 1, it will be greater than or equal to Sn. That is, the sequence is an increasing sequence. So we have proved that the sequence is bounded and the sequence is an increasing sequence. Now if the sequence is bounded and it is increasing, then the sequence is convergent. Now we need to find limit of the sequence. So we'll take this limit n tends to infinite, and suppose the sequence converges to this limit L, we can write L equals under root AB square plus L square upon A plus 1. Now we square it, we'll get A plus 1 L square, and it'll be AB square plus L square Now from here we can write value of L is B. So the limit point of this sequence is simply B, and that is the answer to this question. Now here the question is, show that the sequence Sn, where Sn is 1 upon n plus 1 plus 1 upon n plus 2 up to 1 upon n plus n is a convergent sequence. Now what we'll do is we'll write Sn plus 1 minus Sn. Now Sn plus 1 will be 1 upon n plus 2 plus 1 upon n plus 3, and it will go all the way up to 1 upon 2n plus 2, and then minus 1 upon n plus 1 plus 1 upon n plus 2 up to 1 upon 2n. Now these terms, they'll cancel. So we'll get Sn plus 1 minus Sn is 1 upon 2n plus 1 plus 1 upon 2n plus 2 minus 1 upon n plus 1. Now we can write this as 1 upon 2n plus 1 minus 1 upon 2n plus 2. So it will be 1 upon 2n plus 1 into 2n plus 2, which is greater than 0. So from here we can say Sn plus 1 will be greater than Sn, that is, this sequence is an increasing sequence. So this sequence is monotone increasing. Now we need to prove that the sequence is bounded. Now we know that Sn will be greater than 0, and this Sn, which is 1 upon n plus 1 plus 1 upon n plus 2 plus 1 upon n plus n will be less than 1 by n plus 1 by n plus 1 by n, that is n times. That means this Sn will be greater than 0 but less than 1. Now since the sequence is monotone increasing and bounded, we can say that this sequence, it is a convergent sequence. Now we have to find limit point of the sequence. We can write this sequence as limit n tends to infinite Sn, and it'll be this limit n tends to infinite this summation 1 upon n plus r, which we can write as limit n tends to infinite this summation r varies from 1 to n 1 by n 1 plus r by n. So we can write this as this integral dx upon 1 plus x when x varies from 0 to 1. It will be nothing but log 1 plus x from 0 to 1. So this value will be simply log 2. Now here the question is, show that the sequence Sn, where Sn is 1 upon factorial 1 plus 1 upon factorial 2 up to 1 upon factorial n is convergent. Now what we'll do is we'll find Sn plus 1 minus Sn will be 1 upon factorial 1 plus 1 upon factorial 2 up to 1 upon factorial n plus 1 minus 1 upon factorial 1 plus 1 upon factorial 2 up to 1 upon factorial n. Now this value will be simply 1 upon factorial n plus 1, which is greater than 0. So from here we can say Sn plus 1 will be greater than Sn, that is, this sequence is an increasing sequence. Now we'll prove that this sequence is a bounded sequence. So this Sn will be greater than 0, and it is 1 upon factorial 1 plus 1 upon factorial 2 plus 1 upon factorial 3 up to 1 upon factorial n. Now this is less than or equal to 1. This is less than or equal to 1 by 2. It is less than or equal to 1 upon 2 square, and it is less than or equal to 1 upon 2 to the power of n minus 1. Now if we take this limit n tends to infinite, we can write this Sn will be less than 1 plus 1 by 2 plus 1 by 2 square up to infinite, which is nothing but an infinite GP. So this Sn will be less than a upon 1 minus r, that is, this value of Sn will lie between 0 and 2. So this sequence, it is monotonic increasing and it is bounded. That means this sequence is a convergent sequence. Now we need to find limit of this sequence. Now we take this limit n tends to infinite. So this limit n tends to infinite Sn will be 1 upon factorial 1 plus 1 upon factorial 2 plus 1 upon factorial 3 up to infinite. Now if we add 1 and subtract 1, now this is nothing but this is expansion of e. So limit of the sequence will be simply e minus 1. Now here the question is, let Vn be a sequence defined by V1 equals 1 and Vn plus 1 equals Vn square plus 1 by 5 to the power n whole root. Then we need to find limit n tends to infinite Vn. Now we can write this expression as Vn plus 1 square minus Vn square, and it will be equal to 1 by 5 to the power n, and will be greater than 0. From here we can write Vn plus 1 will be greater than Vn, that is this sequence is monotonic increasing sequence. Now we can write V2 square minus V1 square will be 1 by 5, V3 square minus V2 square is 1 upon 5 square, and then Vn square, Vn minus 1 square will be 1 upon 5 to the power n minus 1. Now we'll add everything. We can write Vn square minus V1 square, which is 1, and it'll be 1 by 5 plus 1 by 5 square up to 1 upon 5 to the power n minus 1. That is Vn square is 1 plus 1 by 5 up to 1 upon 5 to the power n minus 1. Now this is nothing but a GP whose sum is a into 1 minus r to the power n upon 1 minus r, which is 1 minus 1 by 5. Now we take this limit n tends to infinite. This value will be 0. So this value will be simply 5 by 4. So limit n tends to infinite. Vn square is 5 by 4. Then this limit n tends to infinite Vn will be simply under root 5 by 4, and that's your option B. Now here the question is, two sequences xn and yn, they are defined inductively by x1 equals 1 by 2 and y1 equals 1, where xn is under root of xn minus 1 into yn minus 1, and 1 upon yn equals 1 by 2 1 upon xn plus 1 upon yn minus 1. Now we need to prove that xn minus 1 will be less than xn, which is less than yn, and it will be less than yn minus 1, and we have to deduce that both the sequences converge to the same limit L, where the value of L, it lies between 1 by 2 and 1. Now what we'll do is, in the first part we'll prove that xn is less than yn using principle of mathematical induction. Now we'll prove it for n equals 1. For n equals 1, x1 is 1 by 2 and y1 is 1, that is x1 is less than y1, that means p1 is true. Now we'll assume let pk be true, which simply means xk will be less than yk. Now using this relation we can write xk plus 1, it is equal to under root of xk into yk, that is xk plus 1 is geometric mean between xk and yk. That means xk plus 1, it will lie between xkn yk. Now from this one we can write 1 upon yk plus 1 equals 1 by 2 1 upon xk plus 1 plus 1 upon yk, that is yk plus 1, it is harmonic mean between xk plus 1 and yk, that is yk plus 1 will lie between xk plus 1 and yk. So we can write xk is less than xk plus 1 will be less than yk plus 1 and will be less than yk. Now from this we can say p k plus 1 is true. That means from mathematical induction we can say that xn will be less than yn, and if we use this entire result we can simply write xn will be less than xn plus 1 will be less than yn plus 1 and will be less than yn, or in other words we can write xn minus 1 will be less than xn, which is less than yn, which is less than yn minus 1, and this is what we need to prove. Now from this result we can write x1 is less than x2 is less than x3 and it is less than xn minus 1 and it will be less than xn, which is less than yn minus 1, less than yn minus 2 and less than y1. Now the value of x1 is 1 by 2 and value of y1 is 1. So both the sequences xn and yn, they are bounded sequence. The sequence x, it is bounded and it is monotonic increasing, whereas the sequence yn, it is bounded and it is monotonic decreasing sequence. Now both the sequences xn and yn, they are bounded and they are monotonic. Thus both the sequences, they'll converge. Suppose sequence xn, it converges to L1 and sequence yn, it converges to L2, and from here we can write L1 equals under root L1 into L2, and from here we can write 1 upon L2 equals 1 by 2 1 upon L1 plus 1 upon L2. Now from here we can write L1 equals L2. So both the sequences, they'll converge to the same limit, say L, and since we have already proved that both the sequences, they are bounded between 1 by 2 and 1, the limiting value of these sequences, it will lie between 1 by 2 and 1, and that is the answer to this question.